So let's start with the next exercise, which is, if I remember well, just applying Tevna and Norton model on a circuit. So so exercise 7. So the circuit is A, B, R, G, E, and you have an extra R here. So the question is, what is the equivalence model of Tevna and Norton seen for the circuit between A and B? So you just have to apply Tevna theorem or Norton theorem to get the result. We ask you to do this for each circuit for both theorem, but you know that there is a simple way of going from one model to another. So you can make the exercise once, make the circuit once by applying one of this theorem, and once you have at the very end your equivalence model either of Tevna or Norton, you can switch or move from one to another. So I'll let you work on that, and I will just write down the result. So you apply both of whatever method, Norton or Tevna, you want to get the equivalent Tevna generator or the Norton's generator. So here, to simplify maybe even more the circuit, you can consider that this R here is a load, charge en français, that you may remove to try to find the equivalence model seen between A and B, and then you will plug it again at the very end. So quite simple. So let's say either Norton or Tevna lead to RG plus R. And then if you go for, let's say, ETH in that way, you will find that it's equal to E. So at the very end, you have this. A, B, just put the R back, which is the load. And so you can keep going, and you will have something. Oh well, you can stop at this point. That's fine. And of course, if you go and move to the other, Norton model. So now you see that it's so simple to get the final result and even simplify maybe your system. So first circuit, quite easy. If there is no question, you can quickly move to the other circuit. Next page. Here we go, between A and B. In that case, there is no load to consider. So you will, in fact, try to get all of these equivalent to either Tevna or Norton model. Again, I'm just going to write the final result. If you do have questions, go ahead. So this is circuit 2. So the day of the exam, if you have such type of very simple circuits, it should take you no more than, I don't know, like maybe 10 minutes to get the result. So today it won't be the case because you are still in the practice period, but at the very end you should be able to do this very quickly after some training. So you may find the opposite result for ETH or IN, it really depends on the sign, the direction you pick when you are looking at this current or voltage.
Sorry, could you go back to the first slide?
Sure.
Please?
Do you want me to go through it?
Yeah, can you just re-explain how you find yeah, how you got ETH?
Okay, so remember, first thing, removing load. The second thing, finding Rn. For this, you need to turn off the source and see what is equivalent resistor between A and B. So just let me quickly redraw it, and you get something like this. So this, in that case, you have R and RG using because they're both in series, and you're looking for ETH. So you turn on back the source. Let me get some space. So here, actually, you can simplify like this. And you look for ETH between E and B, correct? The thing is, because this here, there is no link between these two here, there is no current flowing here, which means that, in fact, the voltage in between the terminal of this resistor here equals to 0. So at the end, in fact, ETH here equals only to E. Does it make sense?
Yes, thank you.
Perfect.
Excuse me?
Yeah.
You said there was no current. Why?
Yeah. Because there is no link between A and B. You see, this is an open circuit. As soon as you remove the load between A and B, it means that there is no current flowing between A and B. And in this circuit here, in fact, if there is no link between E and B, you have a single mesh circuit, which is open.
So that means that like the current where the wire is supposed to be the same as there's no wire, it's 0?
Yeah, well, as soon as it's open, a branch where the switch is open or where there is no wire connection between 2 points, it means that there is no current flowing between these 2 points. But it doesn't mean that there is no voltage between these 2 points. Okay? And this is here a good example. You see there is no connection, no wire connection between A and B, so no current flowing, but I'm looking for the voltage between these 2 points. And at the end, I found that this voltage equals to E. It's something else than 0, so it's not 0. So it bring you back to a previous question when you have like points A, B, C, D with various voltages. Okay, you can still apply mesh law here, and because here at this point you may have a lot of positive charge here, a lot of negative charge, so you have a difference of potential, so you have voltages, but you don't have any currents because you have no motion of no possible motion of this charge in between one point to another because there is no wire. Is it clear? This is really important to understand.
Yes, thank you.
Okay, perfect. So feel free to have your lecture document in front of you or the protocol I described previously to start training again, applying Tevna and Norton. Do not forget any step. Do not forget to turn back on the sources once you're looking for IN or ETH. Don't be fooled by the direction between ETH or if you're applying Norton model, link A and B with a wire, go and look for a certain ICC current, and remember that the direction you pick for ICC is going to be just the opposite of IN. If you're done, please move to the second part is autonomous exercise. So, well, this could be done at home on your own. Then you can move to the circuit you see number 3 and play with whatever methods you want to get the current I. If you're blocked at some point, feel free to let me know. So you should be done with circuit 2 at least.
Yes, and also circuit 3.
Okay, so if it's fine, please move to the next circuit.
Sorry, but
Yeah.
on circuit 2, why is R not equal to R over 2?
Because you forget to turn off the sources when you were looking for the equivalent resistor. Because if now you switch off a current generator, it means that you erase the cycle.
Oh, you get something open, so...
So this branch over here is now open. So you don't have to consider anymore this R. So in fact, the only R you see between A and B is this one.
Okay, thank you.
Can we move to the next circuit?
Wait, could you explain how you found IN and ETH?
Which circuit?
Number 2.
So I'm just going for ETH. So here you check ETH now. Same protocol over and over again is to label everything. So you're looking for ETH, which is an unknown. Here you know that I0 is flowing here in this branch. You know that there is no current here in this branch because A and B is not are not linked. Same here, there is no current here, which means that sorry? So I0 is flowing here. So then you finish labeling everything. And then the only unknown is ETH. You need one equation coming from mesh law. So here you have different meshes. You have one mesh is here, another one there, and a large one here. But remember that in that case here you have a current generator, which means that in fact this might be a bit confusing you. This is a current delivered by the generator, but there is some voltages between the terminal of the generator that you don't know either. So applying a mesh law in a circuit containing a current generator is adding you another unknown, and you don't want this. So the only useful mesh law here is this one. So you apply mesh law here, you have ETH, I'm going in this direction, ETH minus E plus RI0 equals to 0. And that's it. Did I do some things wrong? Yeah, because it's minus here. Okay. So this is how to find ETH, and if you go for IN, now of course you're not looking anymore for ETH, up, you link this, looking for ICC in this direction. Now this is not so let me erase everything. Here we go. So back to this, looking for ICC, it means that you have ICC here and ICC there. Then you can deduce, because of the node law, the current flowing here, depending on I0 and ICC. The unknown here is ICC. So what is the current in this direction, depending on I0 and ICC? Waiting for you. What is the value of the current going down as a function of I0 and ICC here in the circuit?
It's I0 minus ICC.
Mm-hmm. So now you have all the current flowing in every branches. You go for labeling the different voltages. So I use receptor convention again here. And now you have to apply again mesh law. Do not apply mesh law in a branch containing a current generator because of the extra unknown you add. So again, the only useful mesh is this one. So if you apply the mesh law here, you will have R I0 minus ICC plus E equals to 0. So you deduce that ICC is I plus E over R. The only difference is once you're gonna transform this, you will have this A, B, So you were looking for ICC from A to B, and so IN is in this direction. And that's it. Is it fine?
Yes, but were we supposed to use Norton and Thevenot law?
Sorry, I didn't get your question.
Are we using here Norton or Thevenot's law?
Model, yeah, theorem,
Yeah.
yes. This is the case.
Okay.
Here we use Norton model to transform all of this into this.
Okay, thank you.
Or this. This is also called the Thevenot or Norton generator. So it seems that Buran and Jonathan doesn't know how to use the chat from Zoom, and they should focus more a bit on the exercise and then discussing with the rest of the class, or me particularly. Question on circuit 3. Everybody was able to find the right model and values?
I mean, I got the opposite, but you said it was normal.
Yeah, it depends the direction you picked for looking for either ETH or IN. So maybe I picked the opposite direction, so that's fine. So if there is no question, we can move to the circuit. So now you can make your own circuit.
We were told to have 3 resistors maximum.
Yeah, that's for the autonomous exercise, but
Okay.
well, you can work.
No, I thought this was an example for this, but it is the next exercise.
No, this is the next one. Yeah. All right. So the question is, what about the current here? So here I leave you the choice of the method you want to use to get the result. Either for the, depending on which one you're going to pick, it's going to be super complex or super simple to solve. Whatever, you can practice all of them. Here is the final result you should get. Just listing here all the method you can use. So Kirchhoff law from the beginning, Norton, Thevenin, superposition, simplification, and Millman. And this is a program of the exam, kind of. You should be able to get whatever parameter from a circuit using whatever, like one of these method. And should be able to recognize which one is going to be the more pertinent one to use. So go for it. Give you, well, depending on the method you use, may take you from, I don't know, 2 minutes to 20 minutes to solve.
I tried Norton and it went quite fast.
Okay, perfect. You get the right result?
I forgot the last step where I had to put it back in and calculate I, but I'm doing it now, and
Okay.
It doesn't seem too difficult.
Okay. So simplification or equivalent circuits, this is the same name for the same method. Then you can practice, pick another method. Try to make the same exercise with the same circuit with all of this method, just again to practice, to feel at ease with whatever model or theorem you're using. We will practice this theorem directly during the lab, during labs. And physically we will demonstrate these theorems. So if you encounter any issue with one of these theorem, please let me know. then create your own circuits. You can look for past exams, pick whatever circuits you want, try to solve these circuits using the method we ask you to apply. Then the only last point we will discuss is the notion of power, which is from now just when you consider the power delivered by a generator, it corresponds to the voltage between its terminal time, the current flowing through it. But you can also consider the power dissipated by a resistor, the so-called Joule effect. It again equals to the voltage between the terminal of the resistor time the current, but because of power is voltage time current, in the case of a resistor, because of Ohm law, you know that U equals to R times I, so you end up with this formula, which is also called effet Joule effect in French, and this is how you cook your pasta at Promologie. Because of the Joule effect, applying a high current through a resistor, which is more like a wire if you open your cooker. So applying a high current through a wire make it heat, and you can cook using this. This is a MasterChef icon also. And with this, well, we have seen everything in this electrokinetic part 1 session. Were you able to find the current at least once using one of these methods? Or do you have are you blocked or completely lost?
I have a similar result, but I probably made a mistake somewhere and I can't find where. I have 6E plus 6R I0 divided by 13R.
So this is a non-homogeneous result. Again, this is the 1 minute you should absolutely take.
I have my result is like yours, but instead of the true is a 6 and the minus is a plus. So it is
okay.
homogeneous.
Okay, sorry. My bad. Yeah, take 1 minute because I will be very strict with this. If your result is not homogeneous, I won't even look at it. So take 1 minute, consider if your result is indeed a voltage. Here you have, you're looking for a current. You have voltages over resistor, which leads you to a current. And here, because of the simplification of the resistor, you're homogeneous to a current. So that's fine.
I mean, my result is homogeneous, but
okay,
it's not the same.
So you may have some sign problem somewhere.
I'll take a look at it.
If you want, you can send me your circuits, take a picture of it, and I can double check where your mistake is.
I'll take a look at it before and try
Okay.
to find the mistake myself.
Okay. Someone else find the right result or not?
Not yet.
Not yet. Still on the computation part. I hope so. Normally, considering all the physics theorem, you should be fine. And like usual, you are kind of blocked by the math. So I'll start applying quickly the simplification theorem to show you how quick it could be. And you see that you end up with a single mesh circuit and only one unique equation. So then you apply mesh law and you should find a good result. Just to say I equals to Elec Ec over R Ec plus R. And then you compute and you should find the results I just cycled you. And the mistake you can make is change the sign of the current source or the voltage source in between each time you switch from Tevna to Norton model. Everyone knows how to handle this circuit, or some of you are blocked even from the beginning, don't know really how to do or to treat this problem.
Yeah, I'm lost.
Okay, so which method did you pick?
Well, I tried to simplify the resistors and use Tivnal, but
Like I did?
I
Because, okay, so from the beginning you were trying to simplify, okay? But could you say something if you start from the beginning? Let's say that, forget about all of this. This was just showing you how to play with the simplification equivalent model, but back here, could you say something about resistors in this circuit here?
we can like simplify them.
And the answer is no. Which one you want to simplify?
But like if we turn off the sources.
Yeah, but if you start turning off the sources, then you are applying either Norton or Tevna model, correct?
Yeah.
Oh, so you were applying Tevna or Norton?
I think so, yeah.
Yeah, because if you start from scratch and try to simplify the circuits, you cannot do something. Why this R here is not in series or in parallel to any other R. So of course, if you go for Norton or Tevna, then you start switching off sources and you have this. Consider this R here as a load. So this is what you get, correct? Then you have R over 2 here. So you see R parallel to 2R. This should be your equivalent resistor, correct?
Yeah.
And if you go through the calculation, then this is the product over the sum. So it's 6R over 7. This is what you find. I don't think I made some mistakes. So then you turn back on your source and you go for either Tevna or Norton model, which is, okay, you are going back to this circuit and you remove the source and you check ETH, let's say. Or you link both and check ICC. Then you have to apply noise law, mesh law through the circuit to get this value. So I think ETH is easier to find than I0, but maybe not. So you have to apply multiple time mesh laws and you should be fine. Is it
Okay, thank you.
okay?
I'll try.
Okay. But here, as you can see, maybe, well, it will lead you to at least a system of 2 or 3, maybe only 2 equations with 2 unknowns. If you start simplifying your results, or maybe here, if you apply Millman's theorem, I think you're going straight to the result.
You mean applying it from the beginning, or?
Yeah, well, Millman's theorem is finding the potential at a specific point. You're applying at the point A. So this is R. Yeah, this is the point A. You can apply it here. So you have since all of them here, you have E there because you have E here. So yeah, should go straight to the result. Try to apply it. It's a good practice. Don't use A and B. Let me show you min-mans to finish. So min-man, check for VC. At this point, I get minus E0 coming from this. Coming from this branch, I have nothing. Coming from this branch, I have nothing. And I have also VD over R. Then I have to consider this, and this resistor. So it makes 2R plus 1 over 2R. So now VD, if I apply min-man here, this gives me VC over R plus E over R over 3 over R. And also, because again, the question is about the current here, VC, which is this voltage, which is this voltage, which is this voltage, equals to, so VC equals to R times I. And with this, you're good. Because if you now use this equation in this equation, you end up with VC equals something. It's going to be a function of I0 and R. And then once you have this result, you use this result here and you find this guy. But again, you should feel at ease with Millman theorem. When you use Millman theorem, you consider points. You consider only the first branches arriving at this point. Check for the different potential. If it's helping you, something you can do also. Let's say that I'm applying here Millman theorem at C, and so I consider this. Let me put some color. I have this branch here. I'm going to call 1. This branch here that I call 2. This branch here that I call 3, and this branch here I call 4. And then you have to consider each time if there is some voltage through them or some current. So for VC, first branch, you have a potential of 0, which is this potential here. So 0 over R. Then you have branch number 2, only a current in the opposite direction, which gives you minus 0. Then branch number 3, you still have 0 over 2R. And last branch, you have VD over R. And then you have only to consider here the resistor, which makes 2 over R plus 1 over 2R. Again, it's practicing. But if you do this, maybe it helps you to not forget any of these resistors here in the denominator of your equation. Millman is the fastest, in such circuit, is the fastest method you can use, but it's a big source of mistakes, or sometimes you miss some branches, so you really have to pay attention to to this theorem. But if you know how to apply it correctly, then you go straight to the result in no time. All right, I think we are good for today. Keep practicing on these circuits, all the method you know now. If you have problems, feel free to let me know, to send me an email, to take some picture on your circuits at the point you are blocked, so I can help you. Next time we will make some the next exercise considering the concept of power, and keep practicing again the different theorems. Maybe we'll work on past exam, I don't know. All right. Have a good day, and we meet on Friday, I think.